Hello everyone, in this video I will share with you what I learned regarding the fractional Brownian motion. So let's begin by looking at the very foundation of classical finance, standard Brownian motion. As we can see here on the screen, this classic jagged random walk rests on four defining pillars. First, it has continuous paths. If you look at the magnifying glass here, notice there are no sudden jumps or teleports. The path is entirely continuous. Second, the increments are normally distributed. It's a completely fair game built on a bell curve with mean zero, meaning there's no inherent upward or downward drift. Third, we have independent increments, so the process is completely memoryless. The past path you see here gives absolutely zero predictive clues about the future. This is actually the mathematical background bedrock of the efficient market hypothesis. Finally, the variance equals time. Our formula is in here shows that variance accumulates to a steady, perfectly linear rate of exactly 1 per unit time. This constant accumulation of quadratic variation is what makes the path so incredibly erratic. But what happens when we move that assumption of a memoryless market? On this slide, we will introduce memory, which gives us two entirely new types of path behaviors: smooth persistence versus this rough oscillations. Here on the left, we have the smooth path. Notice how it sweeps in a non-linear pseudo-trend. This happens because the process is persistent. Past upward moves make future upwards move highly likely. Now let's look at this one here. This is the rough path, and it behaves completely differently. It is anti-persistent, meaning an upward move is almost instantly followed by a downward move. This rapid constant reversal mechanism creates the violent, dense oscillations and extreme roughness you see here. So to understand how this memory actually works, we need to look at the anatomy of interdependence, the fractional Brownian motion covariance formula. This t to the power of 2h, and this also t to the power of 2h, they represent the total variance accumulated from the starting origin up to time t and time t big T. Then we subtract the term on the right, this one here, which is the variance strictly isolated between those two specific times. Because of this exact structure, disjoint increments do not mathematically collapse to zero unless our h parameter is exactly 0.5. As it stated here in the bottom, this creates an infinite span of interdependence, so the system remembers everything. So that h parameter we just talked about is the Hertz exponent. Think of it as a dial that controls the span of memory for our process. In here, if we dial down the Hertz exponent down to 0.1, this is a highly rough environment. The correlation between increments is strictly negative, resulting in the highly jagged, anti-persistent, and rapidly oscillating path you see. In the middle, if it's 0.5, this is the standard Brownian motion. The correlation is 0, so it's completely memoryless and represents the classical fair game boundary. Finally, on the right here, if it's like almost 0.9, it gives us a highly smooth path because the correlation here is strictly positive, giving the path long memory and allowing it to form sustained, persistent trends. For example, here we can see upward trend. Now, this is where things get a bit more complicated for quantitative finance, because in reality, h, or the Hertz exponent, is not 0.5. So the classical ethos calculus completely breaks down here, because in standard calculus, represented by the crossed out formula here, absolutely requires a fair game. It relies entirely on the semi-martingales, which is a process that is fundamentally unpredictable. But as we just learned, fractional Brownian motion has embedded memory, so making it predictable and instantly violating this fundamental rule. Furthermore, classical models demand that variance scales perfectly linearly in time, or dt, but under the fractional Brownian motion, the variance scales perfectly non-linearly by t to the power of 2h, because this quadratic variation no longer sums perfectly to t. Classical second-order expansion rules completely fail to calculate the risk. So why do we care about this mathematically complicated rough fractional Brownian motion? Because as you can see on this 3D chart, the real-world financial volatility is fundamentally rough. Empirical data shows that financial log volatility perfectly mirrors fractional Brownian motion, calibrated to a Hertz component of roughly 0.1. By embracing this roughness, modern models can naturally generate the exact short-term options volatility skew we observe in live markets. And they do it without having to hallucinate artificial price jumps, which classical models are forced to do. Finally, understanding this roughness solves the long memory illusion. For years, classical statistical tests detected long memory in volatility markets. We now know that there is no long memory. This extreme roughness of H 0.1 simply tricks these tests because they are fundamentally incapable of processing anti-persistence. We can better visualize this. I've made this simple Python script to simulate the fractional Brownian motion path. This is the formula we just saw of the covariance matrix, and at each time we will just differentiate the Hertz exponent of 0.1 if it's rough, 0.5 which is the standard Brownian motion, and the trendy or the smooth is 0.9. So as we saw on the slides, it should be, yes, exactly, the blue one is the rough path. You can see sudden jumps up and down. The 0.9, we can clearly see there is a trend, downward trend, and the orange path is the standard Brownian motion, where we have no memory, so the future doesn't depend on the past. So that was it for this video. Thank you for watching.